All right, so this is section 2. I accidentally went over a little bit in the last one, but we'll start right here again. So this is section 2. We're going to look at work and its relation to energy. All right, so when we do work on an object, because when we do work, we are applying a force, and remember, it has to go in the direction of motion. So we are moving it as well as applying a force. And since it's moving, in some way, then that does affect its energy. If it's just moving, like you're pushing a shopping cart, then that's going to change the object's kinetic energy because the energy of motion is kinetic energy. If you're climbing up to the top of a mountain, you're going to change the object's potential energy because remember, potential energy is the energy of position. Newton's laws and the equations for motion can be used to derive that relationship between work and energy. So if we look at the example here, let's move this out of the way. All right, so in the figure below, a box is pushed across an ice skating ring with a force F. Let's see how this force changes the box's energy. So remember, you're applying a force. So remember, force is equal to mass times acceleration. That's Newton's second law. And then we also have work going on, and work is equal to force times displacement. Okay, so what we're gonna, and remember, acceleration is a change in velocity over a change in time. So we're gonna wind up combining these, and then lastly, kinetic energy is equal to 1/2 mass times velocity squared. So we're going to wind up combining all of these equations and looking at a relationship between work and energy. So what we're going to do is we're just going to go through this. We call it a derivation, where we're just going to take an equation or several equations, and we're going to begin to combine those equations together to come up with another equation. All right, so we know Newton's second law here. This is F equals ma, and we just rearranged it. Whoops. Let's do this. F equals ma, and then we just rearranged that to solve for a. And then we learned in chapter 3 that speed and displacement of an accelerating object is equal to this equation. So the final velocity of an object is equal to its initial velocity plus 2a times its displacement. So again, that's relating speed and displacement. With a little bit of rearranging of this equation, we get 2ad equals vf squared minus vi squared. And then if we take this is where we're deriving things. So we take that acceleration is equal to force divided by mass, and we plug into that equation. So let's see, that would be 2f over d times d. So that means, is that right? Oh, no, that's not right. Hang on. Erase that. Vf squared minus vi squared. Okay. And then we replace a with, that's what we did here, with 2f over m and multiply both sides of the equation by m over 2 because we want to simplify this down. So we're just going to take this part, multiply both sides of the equation by the inverse of that. So that cancels out and we're left with f over d. And that's equal to 1/2 mvf squared minus 1/2 mvi squared. And then we remember that, okay, work is equal to force times distance. So now I can say work is equal to 1/2 mvf squared minus 1/2 mvi squared. So we derived an equation for work based on speed and mass because of the other equations that we know, that we learned earlier. Okay. So you're not going to have necessarily enough to know how to derive equations, but you do, It just gives you a little explanation of how we get to the equations that you're going to have on your test. All right. So from this relationship, work is equal to 1/2 mvf squared minus mvi squared. We see that work done on the box is related to this quantity, 1/2 mv squared. So now we can relate that to kinetic energy. So that quantity, 1/2 mv squared, is the kinetic energy of the object. Okay, so we can say that work is equal to a change in the kinetic energy of the object. Because kinetic energy is 1/2 mv squared. Okay. In general, kinetic energy is the amount of energy due to its motion. And again, is measured in joules, just like work is. And there gives you some examples of different amounts of kinetic energy for different motions or movements. Kinetic energy increases linearly with mass and with the square of the velocity. So if you look back at the equation, kinetic energy is directly proportional to mass and directly proportional to velocity squared. And this just gives you a little bit of an example of that. So we take a 3,900 kilogram truck moving at 6 meters per second. What is its kinetic energy? So we just plug and chug into that equation. So 1/2 times 3,900 times 6 squared. Don't forget your squaring. That'll be an easy place to make a careless mistake. And it's 70,000. And then we double the speed. What's going to happen to the kinetic energy? So if we double the speed, everything else is going to stay the same. We're just doubling the speed. That means it's going to be a factor of 4 times greater, because 2 times whatever that speed is, remember we're squaring it, so that's going to mean that it's 4 times greater. So we can just take our answer from A and multiply by 4, and that tells us that our kinetic energy will be 280,000 joules. So 4 times greater because of that square factor. This is what we call the work energy theorem, and I put that on the screen earlier, that the total amount of work done is equal to the change in kinetic energy. Because remember, anything final minus initial is always change in. So we can say this is just equal to change in kinetic energy, remembering that kinetic energy is 1/2 mv squared. Okay, all right. So here's an example. How much work is required for a 74 kilogram sprinter to accelerate from rest to a speed of 2.2 meters per second? So if he's accelerating from rest, that means that his initial velocity is 0 meters per second squared. And we're just going to plug into the work energy theorem. And so 1/2 times 74 times 2.2 squared minus 1/2 times 74 times 0 squared, which again, if that's 0, that whole thing's going to fall out to 0. And it's just going to be based on this final speed, which would be 180 joules. All right, the sign of work is related to the change in kinetic energy. So again, remember we say work could be 0 or positive or negative. So if total work is positive, that means that your kinetic energy is increasing. If total work is negative, then that means your kinetic energy would be decreasing, because the 1/2 mv initial term would be greater than the 1/2 mv final term. So if we go back and put this back up here, final squared minus 1/2 mv initial squared. So in order for work to be negative, this would have to be the larger term. And if work is positive, then this would be the larger term. And if work is 0, then there would be no change in kinetic energy. So your two velocities, initial velocity and final velocity, would have to be the same number, meaning it's not speeding up at all. It's going at a constant velocity. Okay, so the following is an example of that illustrates work energy theorem as applied to an object that has an initial speed. So the one we did before, it was starting from rest, so our initial speed was 0. So this time, though, we're not starting from rest. A boy does 19 joules of work when he pulls a 6.4 kilogram sled through a distance of 2 meters. No other work is done on the sled. If the initial speed of the sled is 0.5 meters per square, 0.5 meters per second, what is the final speed? So remember, we are looking for the final speed now. So what we're going to do, and what is probably going to be better for you to get in the habit of doing, is rearranging this equation before, before you put numbers in. So let's just practice the algebra with that. All right, so we're trying to get that guy by itself, which means that I need to get rid of this term right here, okay? So since that is being subtracted, and I'm going to do it a little bit different way than the way they did, but since this term is being subtracted, the way to get rid of it, to do the opposite, is to add it to both sides. Okay, so that's going to leave me with 1/2 mv final squared equals w plus 1/2 mv initial squared. Okay, and then so now I have this part that I need to get rid of, the 1/2 m. So since they're multiplied, the way I'm going to get rid of that is I'm going to divide by 1/2 m. So that's going to leave me with Vf squared is equal to 2 W over M plus, now these terms here, these are going to cancel for the 1/2 and the 1/2 and the M, so that's just going to leave me with Vi squared, okay? Then lastly, I need to get rid of that square, so I'm going to take the square root of both sides. So Vf is going to be equal to the square root of 2 times the work divided by the mass plus Vi squared, okay? So once you get your equation derived for what you are actually looking for, then it's a little bit easier and you can just plug the numbers in and do the algebra on that part. But doing this way too helps me be able to just go back and double check my algebra a little bit before I start putting those numbers in. Okay. So as the figure below indicates, work must be done in lifting the bowling ball from the floor to the shelf, even though the ball has no kinetic energy once it's resting on the shelf. The work done in lifting the ball is not lost, it's stored there as potential energy. So remember, energy and matter cannot be created, cannot be destroyed. So I'm doing work when I lift the ball and I put it up on the shelf. While that ball is moving, it also has kinetic energy because I'm moving it. But once I put it on the shelf and leave it there, what happens to that kinetic energy? It can't just disappear. So what it does is it converts into potential energy because now it's at the top, it's above the Earth's surface, it's sitting on that shelf. And so it has the potential to fall off and come back to Earth or back to the surface. So it has potential energy. If that ball were to roll off the shelf, at the point where it rolls off, then that potential energy is going to wind up getting converted back into kinetic energy. Okay, so the work is still there. The work stays the same. It's the energy that will get converted between kinetic energy and potential energy and back again, depending on where that ball is and what it's doing. So remember, energy does not get lost. It just changes forms. And so the work done doesn't get lost. It just changes forms. Energy is stored for later use and referred to as potential energy. Potential energy has several forms. So the one we're going to use the most or talk about the most is what we call gravitational potential energy. And gravitational potential energy equals the work required to lift an object to a particular height. Because when you lift it up, you're moving it, and then your height above the surface of the earth is what gives it that potential energy. So lifting the mass from the ground to a height of h requires a force, mass times gravity. Because remember, weight, the weight of that ball is its mass times gravity. And when you're lifting it up, you're having to overcome that gravitational attraction. So the work done then um, has to be equal to the force due to weight times the height above the object, above the surface. So it becomes mgh. So work done in that situation is equal to mgh. So remember, our original equation for work is force times distance. So now our force just becomes force due to weight. Our displacement becomes the height at which we're moving it. Okay, and so potential energy then is also equal to mass times gravity times height. Remember that work energy theorem says that work is equal to energy. So same thing here. Work is equal to potential energy, gravitational potential energy, which is equal to mass times gravity times height. Objects like rubber bands and springs often return to their original size and shape after they've been distorted. If something does that, we say that it's elastic. Stretching a spring requires work because, again, you have to apply the force and it is going to move a distance. So that's work. This work is stored in the form of potential energy, the spring's potential energy. So the potential energy stored in an elastic material is referred to as elastic potential energy. And that's related to Hooke's law. So if you go back and remember, Hooke's law is 1/2 kx. So when we move that spring, or when that spring gets distorted from an x position of 0 to some other position, there's a spring constant k. And so that force, Hooke's law, is 1/2 kx. And since we're going to relate that to work, remember work is force times distance. Well, in our case, in this particular case, our force is 1/2 kx, and our distance is x, is the amount that it gets displaced. So our work is 1/2 kx squared. So this is the work that is stored as elastic potential energy. So if we're talking about springs, different things like that, that's the equation you're going to use, not mgh. Okay, it's going to be 1/2 kx squared. All right, and there's our example. So that too is the potential energy of a spring is 1/2 kx squared. Again, because remember, work equals energy. You don't lose any energy. So energy has many different forms. We have mechanical, which has to do with movement. We have electrical, which of course is electricity. We have thermal, and we have nuclear. Okay, anytime work is done, energy gets transferred from one form to another. One process might transform kinetic energy into electric potential energy, or it might transfer it into spring potential energy, into kinetic energy, or something like that. So, anytime work is done, there's an energy transformation that takes place. No matter what that process, the total energy stays the same. The total energy in the universe stays the same because we can't create energy, we can't destroy energy. So energy is always conserved. It just transfers and gets transformed from one form of energy to another form of energy. All right, so along those same lines, frictional forces act on a system like a car's braking system When that's applied, the kinetic energy is transformed into thermal energy or heat energy. In situations where all forms of frictions are ignored, then you have no kinetic or potential energy is transferred um, in the thermal energy. So when you can ignore friction, then none of that kinetic or potential energy gets transformed into thermal energy. So the sum of the kinetic and potential energies is always the same. That's what they want to get at, is that when we add up all these different forms of energy, we add them all together, then that total amount of energy is always the same because the energy has to be conserved. So we can say the total energy is equal to potential energy plus kinetic energy. Okay, and mechanical energy or total energy is always conserved. All right, and that wraps up section 2, which actually I did it again. I went over. Okay, that's okay. Just one slide over. All right, so that is it for section 2. Hope you have a great day.